picking up good vibrations.
In this video, we'll talk about the properties of the Fourier transform. These properties allow us to compute Fourier transforms of elaborate signals from Fourier transforms of basic signals. A very important property is the convolution property. This allows us to exchange convolution in time by a simple multiplication in frequency, a simple multiplication of the Fourier transforms in frequency. This property has many consequences, and we'll discuss this also in this video. The Fourier transform and the inverse Fourier transform formulas are given here. These define a one-to-one transformation between any signal x of t and a Fourier transform capital X of j omega. We can then call x and capital X a Fourier transform pair. And this will be denoted from here on by this notation, a two-sided arrow with a calligraphic capital F on top. For instance, we can say that the Dirac in time and the constant function 1 in frequency are Fourier transform pairs, and other examples are also given here. Let us start with a very simple property of the Fourier transform, linearity. If we have two signals, x of t and y of t, and corresponding Fourier transforms capital X of j omega and capital Y of j omega, if we take a weighted sum of x and y, if we consider alpha 1 times x of t plus alpha 2 times y of t, the Fourier transform of this weighted sum will also be the same weighted sum of the Fourier transforms of the original signals capital X and capital Y. So basically, alpha 1 times capital X of j omega plus alpha 2 times capital Y of j omega. Now, this is straightforward to derive mathematically. We just have to plug in alpha 1 times x of t plus alpha 2 times y of t in the formula for the Fourier transform. If we do that, and if we simply rely on the linearity properties of the integral, we'll get alpha 1 times the Fourier transform of x and plus alpha 2 times the Fourier transform of y. Why is this useful? Let us say that we know by heart the Fourier transforms of two signals, let us say a cosine and a constant, and we want to know the Fourier transform of the sum. Then that will simply be the sum of the Fourier transforms. Time shifting. This is another very, very useful property. If x of t and capital X of j omega are Fourier transform pairs, and if we consider the signal x of t minus t naught, so a delayed version of our signal, the Fourier transform of that delayed version will be capital X of j omega, the original Fourier transform of x, times e to the power of minus j omega t naught. So a delay in time corresponds to a multiplication by e to the power of minus j omega t naught in frequency. And note that this complex number, e to the power of minus j omega t naught, has magnitude 1, so we do not affect the magnitude of the Fourier transform when we shift the signal. T naught might also be negative, and this property still holds. Now, deriving this property mathematically is again very, very easy. We just have to plug in x of t minus t naught in the formula, in the Fourier transform formula, and if we apply the change of variables t prime equals t minus t naught, we obtain that the limits of integration remain the same, dt equals dt prime, but when we replace t by t prime plus t naught, we get exponential of minus j omega t plus t naught, which is exponential of minus omega t times exponential of minus omega t naught. And since exponential of minus j omega t naught does not depend on time, we can move it out of the integral and we obtain exponential of minus omega t naught times the Fourier transform of x, capital X of j omega. Now, let us use this shifting property to derive the Fourier transform of a sine if we know the Fourier transform of a cosine. So, sine of t equals cosine of t minus pi over 2. So we know that to compute the Fourier transform of sine of t, we just have to consider the Fourier transform of cosine of t and multiply that by e to the power of minus j omega pi over 2, which is t naught. Now, the Fourier transform of a cosine are two Diracs, so by multiplying by e to the power of minus j omega pi over 2, we just have to consider omega at values where these Diracs are centered. And if it's a cosine of t, they are centered at omega equals 1 and omega equals minus 1. Once we multiply this Dirac by omega minus j 1 pi over 2, we get that this direct is also multiplied by e to the power of minus j omega pi over 2 when omega is 1. And that's basically minus j. And when we multiply by the direct centered at minus 1 by e to the power of minus j omega replaced by minus 1 pi over 2, we are basically multiplying by e to the power of j omega pi over 2, and this is basically j. And so with a few manipulations, we get the expression that we have already encountered for the Fourier transform of a sine. Now, time scaling, this is again an important property if we consider the signal x of at, where a, for instance, is larger than 1, or a can be anything. We obtain a Fourier transform, which is 1 over the absolute value of a times capital X of j omega over a, where capital X is the Fourier transform of the original signal x of t. Now, if a is larger than 1, we are shrinking the signal in time, and that means that we are stretching the signal in frequency. If a is smaller than 1, we are stretching the signal in time, and we are shrinking the signal in frequency. This property is also very easy to derive mathematically. If we plug in the Fourier transform formula x of at, and we apply the change of variables t prime equals a of t, a times t, for positive a, let's start with positive a, we get the same limits of integration from minus infinity to plus infinity, and we get now that dt is equal to dt prime over a. So we must replace as well t by t prime over a, leading to the formula 1 over a times capital X of j omega over a. Now, if a is negative, the limits of integration will switch, and to switch them again, we need to multiply by minus 1, and this is why we see the absolute value in the formula. Now, here's an example. Say that we have a double-sided exponential, which has this Fourier transform, and that we've seen in a previous video. Let us say that we want to scale this signal in the time domain, so now by consider exponential of minus absolute value of t, minus a times absolute value of t, then the Fourier transform is obtained by changing omega to omega over a and dividing the CL by 1 over omega. If omega is positive, that's what we are considering here. Now, a property that by itself might not seem that important, but has several consequences, is that if x of t and capital X of j omega are Fourier transform pairs, then the complex conjugate of x complex conjugate of t, corresponds and as a Fourier transform pair with capital X complex conjugate evaluated at minus j omega. Now, I was saying that per se is not that important because we rarely find signals that are not real, that are complex. But so this is a property that tells us how to compute the Fourier transform of the complex conjugate of a signal. This formula is also mathematically very easy to derive. If we plug in x complex conjugate in the formula for the Fourier transform and take the complex conjugate, we get that the complex conjugate of the integral is the integral of the complex conjugate, and the complex conjugate of the product between x complex conjugate and exponential of minus j omega t is the complex conjugate of the complex conjugate of x, which is nothing more than x, times the complex conjugate of e to the power of minus j omega t, which is e to the power of j omega t. Then this is nothing more than the Fourier transform of the original signal evaluated at minus j omega. The consequences: if x is real, then the complex conjugate must be equal to itself, so that capital X of j omega must be equal to the complex conjugate of minus j omega. Or in other words, x of minus j omega must be equal to x conjugate of j omega. This leads to some important conclusions. The first is that if we know x of j omega for positive omega, we also know x of j omega for negative values, minus j omega. And this is because when omega is negative, we can just get x of minus j omega is equal to capital X conjugate of j omega. The second important conclusion is that if we take the even part of a signal x, then its Fourier transform is the real parts of the Fourier transform of x, the original signal. In turn, if we take the odd parts of a signal, then its Fourier transform is j times the imaginary part of the Fourier transform of x. In particular, if the signal is even, then the Fourier transform is purely real. If the signal is odd, the Fourier transform is purely complex.